Hello, everyone. So although we have discussed evaluation criteria of searching strategies, but I want to reiterate this, so I'll go through all of these criteria once again. So the first one was completeness. Uh, and we would say that a searching strategy would be complete if it is guaranteed to find a solution given there exists one in the graph. So by that, I mean that let's say if you talk about breadth first search, I know that for each parent, I should explore all of its children's first before going down towards the depth of the tree. Okay, and imagine that if there is a situation where, for example, you're not sure about how many children a particular node can have. Okay, so in that case, we would say that our branching factor B is infinite. Okay, and by that I mean that I'm not sure. Let's say, for example, this node C can have unlimited number of children, and one of that child can be your goal node. Okay, or vice versa. The goal node can exist anywhere, but if there is a case where any child has infinite number of children, then breadth first search is incomplete, because it is bound to explore all children of C first before jumping on towards children of E, for example. And likewise, so if branching factor B is infinite, then this means that BFS, breadth first search, is incomplete. And likewise, if M is infinite, and by M I mean the maximum depth of a tree. So here the maximum depth of tree is 0, 1, 2, 3, 4, 5. So M is 5 and D is 2. So D is depth of the goal, which is in this case goal node is G. So I have depth D is equal to G is equal to 2. So in depth first search, since I'm going to explore all children that I encounter in a particular path towards down the tree, then I'm sure that if M is infinite, so if I'm not sure that if I go down the tree, where does this path end, for example, I'm not sure what is the maximum M of a tree. In that case, depth first search will be incomplete, because I will I will start going down this path, and I'll be lost in some sense. And so this is the situation where which is encountered more often. And by that I mean, for example, if you are talking about chess, in chess, I'm sure that on average, like I can predict that if I'm any board position, from that board position I can have, let's say, on average 40 or 45 different moves. Okay, so for that parent node I can have, let's say, 45 children. So even though this B is great, but at least I'm sure that it's not greater than 45. But what I'm not sure of is, let's say if I play a particular move and then my opponent, let's say, puts some different move, I'm not sure how many moves would I make to win this match of chess. So I'm not sure of the actual depth of the tree, where the goal resides, or let's say I'm not sure of the maximum number of moves that I would have to get, let's say, to win. So or let's say another example is that, let's say if you have a map and you have to go, let's say, left, top, down, left, right, you have, let's say, 4 options, either to move forward, go backwards, go left, or go right. Okay, so every node would have 4 children in that case. But what you're not sure of, that, let's say if you go left, how many times you have to navigate left, right, top and down, just to reach your goal. Okay, so your goal, there can be, let's say, a huge map, and so therefore what you're not sure of, how many moves would you need, look like what will be the depth of the tree that will get you to your goal. Okay, and so therefore this scenario is more common, where your M is infinite. And so in that case, you should prefer breadth first search rather than depth first search. The second criteria was optimality, and therein we discussed that if we forget about the particular weights of each edge, and I know that moving from A to B is the same as moving from A to C, which is the same as moving from C to F, and which is the same as moving from B to E, for example. Like every every hop has, let's say, an equal cost, then I'm sure short that breadth first search will be optimal. In that case, so for example, if my goal is k, and I'm starting from a, you know, and let's say my the criteria of defining the path to the goal is that whichever path leads me to this goal node k first will be my optimal path. Okay, so this is my definition. The path, like the algorithm which you apply, and the path that you follow in your breadth first search or depth first search, such that that path leads you to your goal. And the first path that you iterate through to reach your goal, let's say that is your solution, or that is your path. So if that is my definition of optimal path, whichever leads me to my goal node first, then breadth first search is optimal. In this case, for example, not in this particular case of graph, but any graph, if you assume that your goal node, the path that leads to your goal node is your desired path, then this will be the optimal path in breadth first search, which in this case will give you A, B, D, and K. Okay, so from A, then you'll go to B, then you go to C, then you'll go to D, and while you're at D, you'll check whether or not any child of D is a goal node, which in this case is true. So you'll return A, B, D, and K as your goal path. But if you run depth first search, let's say from right to left, what will happen is that you'll go to node A, then you'll go to node C, and then you'll go to node F, then then you'll go to node G, and then F. And while you're going to each node, you'll check that whether or not each child is a goal node, which in this case is not true. Then you'll go to node B, E, H, I, and while you're at node I, you'll encounter that your goal node is the child of I, and so therefore you'll have to return A, B, E, H, I, and K as your path, which is obviously not optimal. There exists a path which is shorter in some sense in terms of number of hops. Okay, so even if this is the case where your hop has an equal cost throughout the graph, even in that case, depth first search isn't optimal. Okay. Now we'll see another class of algorithms that takes into account the weight of each hop, and in that case, the optimality will be the definition of optimality will be something different, and we'll see that how another strategy helps us in defining that optimal path from A to K, for example. But at least in comparison of BFS and DFS, breadth first search is optimal, given that each hop is constant throughout the graph in terms of its cost. Right. The third thing is time complexity, and so we are in terms of breadth first search. I know that for each, let's say, if I have to reach any goal node which resides at depth D, then I'll have to iterate through each of the parent nodes that exist until D-1 level. Okay, which means that I'll have to traverse through B to the raised power D-1 nodes, which exist at the depth of the parent. So if my goal is at level depth D, then for example, in this case, I will reach my goal while I'm visiting my parent at D-1. Okay, so I'll have to visit all nodes until D-1 until I get I get to my goal node. Okay, so in that case, your complexity will be order of B to the raised power D-1. But obviously we don't write constant, so in literature you'll see that will be referred to as order of B to the raised power D, but I'm just being very precise over here. So this is the strategy in terms of, this is the complexity in terms of breadth first search. But in depth first search, you see, even if your goal resides at, for example, level D is equal to 2, which in this case your goal can be one of D, E, F, G. But if you apply depth first search, then you'll have to traverse through any path which has the maximum depth of the tree before you reach your goal node. So I'm talking about worst case scenario over here. So even worst case scenario, you'll see that the breadth first search will have the worst case complexity of order of b to the raised power d, but depth first search has the worst case complexity of order of b to the raised power m. Okay, because if your goal node is at depth d, but your maximum depth is m, then you'll have to traverse through different nodes at until you reach your level m before actually traversing up again down the tree and reaching your goal d. So in this case, your time complexity will be order of b to the raised power m. And obviously this means that this depth first search is terrible if your goal is shallow. But depth first search is good if let's say if your goal are dense. If your goal resides at deep down the tree, then perhaps depth first search is in that case less time complex. Okay, but in terms of worst case scenario, breadth first search is good than depth first search. In terms of space complexity, that is defined by auxiliary variables, which means that if I go through this algorithm, I have two lists. One is visited, and the other one is queue. How many nodes would I need to retain in this queue and in this visited list before I reach my goal node? So this will be your space complexity. Now, in terms of breadth first search, while I'm exploring, I have to put my nodes either in visited list or in queue. Okay, so let's say if I'm at level D, I have to put all the nodes that I have encountered until D-1 level into my visited list, and all the nodes that exist at level D into my frontier or into my queue. Okay, that I'm going to explore. So in that case, I mean, I have to save every node in the graph, which is dominated by order of b to the raised power d. Okay, so this means that the number of nodes in my graph can be represented by these 4 nodes. Okay, all the nodes that reside at this level d, because these 4 nodes are greater than all the nodes combined in the previous levels that we have already discussed. So in this case, if you go at any level d, you are sure that all the nodes combined until d-1 are less than the nodes existing at your level d. Okay, so that is why your space complexity in terms of breadth first search will be order of b to the raised power d. But in terms of space complexity, depth first search is good. But this implementation that I have written in here, where you simply replace your queuing strategy, and that's it. This is in terms of space complexity exactly equal to BFS. Okay, but we can be clever if we use recursion, which we'll see in dynamic programming perhaps next week. So you can use recursive strategies for your depth first search, and by that I mean that you can start from your node, jump to the left node, and then jump to its left node, and then jump to its left node. And while you're jumping, save your parent node in your visited list, and the second child which you have not explored, put that child in your queue. Okay, the list that is going to save your to be explored nodes. Okay, so if you follow this strategy, once you are at leaf node, so you have your function which you use to go to your level, to go to your child of A, and then go to your child of D, and then go to your child of D. And then once you encounter a leaf node, your call stack will return. And when I say that your call stack is returned, I mean that the functional space will be destroyed from memory. Okay, so that this means that your variable, or let's say the space allocated to that function, which in this case was just holding one node edge, that will be destroyed. Okay, and so once you recurse from D to B, you'll see that you'll all like the graph, all the children of D will be destroyed from the call stack. So when the in recursion, when when you recover from your call stack, when you move from bottom up, the actual space of allocated to that function will be destroyed from memory. And so therefore, the worst case scenario in this case is, for example, this case wherein you have to space where you have to store basically 2 children per level, okay, and you have m levels in your tree. And if you have 2 children per level, then that means that you need to save 2m nodes in your memory. And if you have b children, then this means that you'll need to save bm children in your memory, okay. So in this case, 3 nodes will be in your visited list and 4 nodes will be in your queue, okay. So this means that space complexity, if you use recursion, that will be linear with m, okay, which is far better than exponential with d. Even if d is less than m, exponential space complexity is really very bad, but linear is good in some sense. Okay, so in terms of space complexity, depth first search is good if you follow recursion, not if you follow this approach that we have discussed. Okay, so this concludes the four evaluation criteria of searching studies. We will then in the coming video we will discuss shortest pass first, and then perhaps its complexity as well.